So I'm just using spherical coordinates. One little problem. Of course, that's two variables, but when I get to x, I'm going to have three variables. Rho, sine phi, cosine theta. I can't use three variables. I only get to do two on a surface.
So you substitute Z?
What now?
Substitute Z?
Substitute z, well, it's still no good.
We could do W equals rho.
No, let's not do w equals rho. Because we already have one variable. We don't need to put another one in there, but how about a?
How about it?
So this thing is rho squared. So rho squared, rho equals a. Yeah, that's the equation of a sphere in spherical coordinates. Again, it's not the equation of this sphere over here, but it's the equation of any sphere centered at the origin. And of course,
So you just plug in an A instead of rho.
I just plug in an a instead of rho. Just like we were doing x equals a cosine theta and y equals a sine theta when I did circles, right? I said I'm going to use polar coordinates, but I only get to use one polar coordinate. The other one I have to hold a constant. So now here's the confuser. Now I'm going to use R because they use R as the generic vector valued function for all these surfaces. And they also use it as the generic vector valued function for all these curves in the other chapter. But anyway, R of phi and theta, instead of u and v, I'll call it phi and theta, equals xi plus yj plus ck. And notice something here. All of these have a factor of a.
A is a constant though.
And a is a constant,
So that's okay.
and that's okay. I mean, it would actually even be okay if it was a variable. I mean, like if it was phi, I could have a constant. But what I want to do is to bring the factor out front. So this is going to be cosine phi,
Oh, kind of.
cosine theta, kind of like a common factor.
Yeah, no, I'm thinking in terms of linear.
Oh, you mean like
So it's like R times like a vector. Or something.
yeah. So what's it called? Multiplication of vectors plus
Yeah.
scalars. There you go. That's exactly what it is. By the way, there will be a new supplement about surface intervals up there. I may not put it up before Thursday.
Right now?
No, it's not up there yet. I may not put it up there before Thursday. And it will have some of this stuff. It's not going to go into details, but it's in the problem format. So one of the problems is, hey, go out ahead and work out everything about surface area stuff for a sphere. And hey, then we're going to do another surface. But anyway, so you'll see these formulas summarized on that. So now, if I want to do surface area, I'm going to have to get with the program here and calculate partial derivatives, and then take the cross product of the partials and the magnitude of the cross product and blah, 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 blah.
So in this case, it's like R sub phi and R sub theta.
So we might as well do that. A is a common factor, and it's a constant common factor, so
Yeah.
that'll be a product rule.
That would be negative sine of.
Well, except that I didn't write it correctly. It's supposed to be sine.
Oh, so
Yeah, I thought so.
Sine, cosine, sine, cosine.
we failed you, though. We failed you. We should caught.
Yes, I know. I was testing you. Here we get a minus. Is that believable? So let's see, phi, that's the co-latitude, right? Phi is 0 at the top, 90 at the equator, 180 at the south pole. So here are my meridians. Theta is constant on a meridian, but phi increases from top to bottom. So in the top half of the sphere, phi is increasing and the point is moving outwards. And so x, let's take the first octave where x is positive and y is positive and z is positive. So as phi increases, the x is increasing and the y is increasing and the z is decreasing, right? Plus, minus.
Yes, I see that.
All right. Now, if we're over here in the western hemisphere where theta is negative and also y is negative, well, if theta is negative, the sine will be negative. And so what's going to happen here is that the x will be decreasing.
Yeah, the x will be negative.
Yeah, the derivative for the x will be negative.
So y will be positive, and
Negative, yeah, okay.
then the other one is unchanged. It will stay positive.
And then down in the southern hemisphere, where phi is greater than 90, then our cosines and sines are, well, let's see. So down here, this will be, this will still be negative, because sine is positive between 90 and 180, but these cosines will be negative. So it'll be coming back in. All right, r sub theta. And so I'm still going to have this thing. And I'm going to start abbreviating the abbreviations again. So that's going to be a minus the sine. So minus cosine phi sine theta I. And this will be plus cosine phi cosine theta j. And what about there?
That's gonna be 0.
That's going to be 0. Plus 0, minus 0, who really cares? So now, that means that I've got another, by the way,
Yeah, let's say, I got that wrong.
you were going to say you just wouldn't. Well, how kind of you to let me discover my own mistakes. All right, so anyway, I needed to not be looking here, I needed to be looking up there. And so, yeah. So now, what I knew was that the sine was going to factor out. And then when I saw it was a cosine, I said, oh, that's a mistake. So anyway, this will be a sine phi, and then it's minus sine theta I plus cosine theta j. All right. So here goes. Cross product n is r sub phi crossed with r sub theta. And, all right, we got a, and it's sine phi cosine theta I. Oops, no, cosine phi. I'm doing r sub phi first.
Or cosine.
So cosine phi cosine I plus cosine phi minus plus,
This plus.
it is plus sine theta j minus sine phi j. Then cross that with a sine phi, and this is minus the sine of theta plus the cosine of theta. And let's see, my scalar factors, the a and the a sine phi, I just pull them out front. So I get a squared sine phi. Oh, look how sweet that is. That's like in the volume form that we have. Except that it's not a volume form because we don't have any depth. But it's what we would get from this if I substituted A. And then I will leave this one to you, basically. But I'll just point out here, like we've got, what, K cross J, right? K cross J is what?
Negative I.
It's negative I. But there's already a negative,
Positive.
so I'm going to get positive. And this will be sine phi cosine theta I.
But you started at the end.
And then, and I haven't made any mistakes on this one yet.
No, I'm asking why you just started at the end. Just
Because I wanted to get an I thing, because that's what comes first.
Oh, okay.
That's also the way I do curls. Anyway, so now if I wanted, is there another I term? Well, no, because there's no K term here. I could do J cross K would be a positive I, but there is no K term. So then I go for the J term, and
You do that last one with the sign?
yeah, so right here.
Yeah.
So I've got a plus, and then K cross I is
Still positive. J.
still positive. So here's a plus, and it's gonna be,
Sine phi, sine theta. J.
and then, I said I was gonna leave this one to you, but I guess I'm doing it. Here we've got an I cross J is K,
Yeah.
and a J cross I is minus K, but there's a minus there.
So,
So it'll be positive. And I'm gonna get a cosine phi, cosine squared theta, and I'm gonna get a cosine phi, sine squared theta,
ooh, no, I see it.
and it's plus plus, because here I had plus minus, but it was J cross I is negative K.
Do cosine phi, K.
And now look at this.
Mm-hmm.
That's the same as the original R. Except the coefficient, the scalar factor is different. What's going on? Okay, I've got a sphere. And consider the fact that any radial line is perpendicular to the tangent plane of the sphere. Just like any radial line on a circle is perpendicular to the tangent line of a circle. And then, so that means it's perpendicular to the phi derivative and to the theta derivative. So when I cross product the phi and theta derivative, the cross product has to be perpendicular to those, so it has to be a continuation of this guy. The length might be different, but the direction's the same. So that's kind of cute. And spheres centered at the origin are the only surfaces that work this way. So anyway, getting close. Magnitude of n. Well, this is just a scalar, constant scalar factor here. So, and it's positive, so I don't even need an absolute value. So I get a squared sine phi. And what's the magnitude of this? And do you really have to calculate it?
Magnitude of.
Because look, remember this inside part was the same. We had A times this is a vector that extends from the origin to the surface of the sphere.
So it's A.
So it's A. So this part is
1.
1. Yeah. So this part is 1. Now, you want to calculate it? Sure. Sine squared, cos squared theta plus sine squared theta is 1, and we have a sine squared phi, and then sine squared phi plus cos squared phi is 1. So I can just do that. ds is the magnitude of function n times d phi d theta. So I get a squared sine phi d phi d theta. And so then the surface area of the sphere is the surface integral of ds over the sphere. But that is a squared sine phi d phi d theta. And my limits, it's a sphere. It's the whole sphere. And nothing but the sphere. 0 to 2 pi on d theta. 0 to pi on phi. So we separate this mess out. A squared integral 0 to pi sine phi d phi. Integral 0 to 2 pi d theta. A squared times 2 times 2 pi, 4 pi, a squared. The answer we know enough. And consider, what's the volume of the sphere?
The volume of the sphere.
Mm-hmm.
4/3 IR cubed.
Okay, or you can call it a cubed if you want. I do. 4/3, take a derivative. And if you keep the derivative, you get the surface area. And everybody knows that, all right? That's something that people notice early on, and it works for circles also, every circle. Derivative of the area of the circle is the circumference of the circle. But now we can see why it is. It's because, look, we don't get it over here when we're doing volume, we get a chance to integrate this one, but we don't get a chance to integrate this one over here, so it just remains as a squared. But if we integrated it, we would get 1/3 a cubed. We still have the 4 and the pi. So if we got to integrate it with respect to a, you know, as a increase, then we get our 4/3 pi cubed. And again, the geometric way to see that it happens is the fact that if you consider, you know, spray painting your sphere with a uniform coat of paint, so that we've got a uniform delta R all the way around, so that our change in volume, which is the volume of the paint, our change in volume is basically the surface area times thickness, you know, the dr.
How'd you get the 0 to pi on the feet?
North Pole, South Pole. If I keep on going, if I go past the South Pole, I'll just reuse the same fees, but my thickness will be different. Okay. All right. So, there's our first, I guess, example, our first case study, so to speak. Because that's what these surface intervals are going to be, is case studies and just projects, really. Actually, I don't want to give you that impression too strongly. On this supplement, I will have several problems of this sort. Here is the parameterization. Here's, you know, R is a function of B and theta, or R is a function of Z and theta, if you do a cylinder, or R is a function of U and V, or whatever. So I give you that parameterization. I'm not really going to give you problems in which you have to come up with a parameterization. I will always come up with a parameterization. Of course, if I give you a sphere, you're supposed to know what the parameterization is. Or if I give you a function of x and y, then you're gonna know what that one is too. But anything else, I'll give you the parameterization. And then I will say, part A, calculate del R del phi, or R sub theta. Part B, calculate R sub theta. Part C, calculate calculate n, which is the cross product.
We have like,
So it just, what now?
we have like 2 more tests left, right?
Yeah.
This one, the final?
This one and the next.
This one and the final, yeah. And so anyway, I will step you through it on some of them. And so you'll practice on this thing, you know, right after you get done with the third exam, you go home, you'll get out that supplement and start working through some of these things.
Is there like a place we could look up these problems though? Cause like, I like to do the problems, but I like to also know if I'm doing it right or not.
You want me to start putting the answers right there along with the problems?
Like, I don't use them to like, to just write down the answer.
I will take it under advisement, yes, I will probably do that. We are running short on time. And you know I do give them in separate files.
Yeah.
All right, and it's no secret that since I'm reusing these things from semester to semester.
Cause I'll be honest with you, I didn't work on these past supplements because I didn't have the answers and I didn't know if I was doing it right.
Well, the answers.
Especially the semester one, because it seemed way too easy.
Oh, well, that's good, right?
Not usually.
It was way too easy, and I was like, man, I don't even know if I'm doing it right. I was like, you know what?
Okay, well, I will have to think about that for the future. Just put the answers there at the same time. That way, you know, I so frequently forget to ever put the answers up there. I scurried around this morning trying to put the answers up there. So anyway, that's probably a very good suggestion. Oh, don't you love the challenge?
Well, yeah, it's like,
just-
I want to know if I'm doing it right.
If I'm,
I don't want to just like sit there and write a bunch of crap down. This is
if
not
I'm
wrong.
orders and
Because I messed up like, I don't know, like a 1 back to land or something.
All right, let's refocus here. All right, the next item I want to look at, the other project is more general than this. It's all surfaces that are functions of x and y. And by the way, one example you should do is the sphere. Of course, you have to use symmetry and do the top half and double it to get the bottom half. But that's the top half of the sphere is a function of x and y. And the calculation is rather different. So anyway, you know, I'm a great believer in working the same problem more than once. But anyway. So z equals f of x, y. Oh, by the way, I mentioned that the area then, the surface area of anything, is a surface integral. And so, just like for line integrals, we had 2 types, and the type 1 basically had d a little less there. And if I wanted a more general one, I just put a function with it. And so then, if f of x, y, z isn't 1, then this is not Arclay. But, you know, depending on what it might be, a density, in which case I get a mass. It might be a variable like x, y, or z, in which case I get a centroid coordinate, all that kind of thing. So it's the same deal here. If I could have the mass of a curved lamina. In other words, a curved surface that I'm thinking of as having virtually no thickness. So basically, I'm doing type 1 surface integrals now. I'm just phrasing them all in terms of surface area. Anyway, so
I think your favorite one too.
All right, so if I put the grid lines in like the meridians and parallels of the sphere, I'm looking at lines at curves that stay parallel to the two coordinate planes, so this would be a curve of constant x. And then here's some curves of constant y. And then these are gonna be my grid lines, like over there. So what I'm gonna do, over here, I had a variable u and a variable v, and when I held one of those unknowns constant, then I got one of these sets of grid lines. But over here, this is a line of constant x. So I'm gonna use x as a parameter. And I'm gonna use y as a parameter. Okay? So, x is gonna equal x, and y is going to equal y. And even in the book, they don't give you this, they just do it this way, x equals x and y equals y. They don't give this nonsense about, well, let's let x equal t, because we don't want to confuse it. X is x and y is y. It's confusing to use two names for the same thing. I'm Alan, and you can call me Fred, whatever, I don't know. But anyhow, so z, what's z? So just like when we had x equals x and y equals f of x, same deal exactly. So, I'm going to do r of what?
X1.
xy. And so r of xy is xi plus yj plus zk, and x, y, and z are functions of x and y. But the x is the x function, and y is the y function, and z is, oh, wait a minute, I don't like it. We're going to call it g. Myself just kind of, for one thing, that will agree with the supplement. And for another thing, I frequently use f as the thing that is the function in my type 1 surface integral.
I got you.
So I'm going to use g for this. And by the way, I'm now working one of the problems on the supplement, which I always do anyway, to work this problem. But on the supplement, it will say, here's the parameterization, work out r sub x, part B, work out r sub y, part C, work out the normal, blah, 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 blah. So, then r sub x equals I'm sort of waiting for you to jump in here.
Like r sub x equals, d, oh, it's just gonna be dx.
dx, wait a minute. This is a derivative, not a differential.
Oh, derivative?
Yeah. So this is del r del x.
Oh, it's gonna be, I, 1 half.
Monocular.
And that's it. That's it.
Really?
Would G
I
prime?
think so.
What?
G prime?
G prime.
Oh, yeah.
So plus, I'm gonna write it as g sub x.
I got you.
That's y.
For the differential.
And then r sub y.
Which is gonna be, j, g sub y plus g sub y.
And I'm gonna quit writing the of x, y's
Hi.
because I'm tired of it.
It's redundant. Well, not redundant, but I don't.
So r sub x cross r sub y, here's part C, I guess it's part C. So I plus g sub x k crossed with j plus g sub y Ooh, binomial times binomial, we can use the FOIL method. So I'm gonna have a g sub y, sorry, I'm just gonna have ij first. I cross j. And then plus g sub y times I cross k plus g sub x times k cross j plus g sub x times g sub y times k cross k.
You know, we're on that last one.
And I don't worry about the last one. All right, so this one's 0. Don't worry about it. It's vector 0. So we get
Okay.
k, and we get
I cross K is going to be negative J.
negative j. And k cross j,
K cross J is going to be negative I.
negative I.
Yes, so she's all you need to do is just rewrite it. Maybe rewrite it.
And I'll rewrite it in good old
But
alphabet.
you write it I in front.
Oops, why did I do that? So equals